Donny Greenberg. My talk is about mobilizing first-party data to build AI systems that beat OpenAI or any other off-the-shelf model in a funny sense that I'll get to in a few minutes. Build better AI apps in general. And I'll note the first half of this talk is about motivating an understanding of what it means to beat OpenAI in a sense, and what it means to build a better AI system. I don't think that there's a kind of well understood working definition for what it means to do better in our space, and I have opinions about that. And then the back half of this talk is actually more about AI systems and what it takes to be able to produce, or rather AI platforms, and what it takes to produce better AI systems systematically. So this is an extremely common starting point for AI talks. I guess it'll be familiar to Jacopo. This is Fashion MNIST. It's a toy test data set that is used in many like machine learning 101 kind of classes or tutorials. The objective, it's modeled off of the classic handwritten digit MNIST data set, but here we're identifying articles of clothing, or we're identifying and classifying articles of clothing out of a relatively small and simple image data set. And the funny thing about this task is that if you use GPT-4o to classify the images, it gets about 81%, which as a proof of concept in a sort of Gen AI prototyping kind of sphere is not bad. But when you compare it to the tree-based model, which is, you know, what 2000s technology, or just a very small like CPU-only ResNet, it's horrifically bad, right? These are models that are trained on tiny devices, require almost no power, and then just like demolish it in accuracy. I mean, the difference from 80-something% to 95% for people who built machine learning systems before is just another level of user success in this case. And the moral of the story is that you have to basically start with the task that you're trying to solve before you begin with a particular implementation or approach. In this case, if you actually look at these articles of clothing, they're not all that easy even for a human to identify. Like if you saw this in isolation, would you know that it was a high-heeled shoe? Maybe not. And so the system here does better with tiny models because it's adaptive to the data. It's not inherently easier for a larger model to identify those images as being a shoe or a blouse or whatever. It's adaptive to the data set, and that's why these models are able to demolish GPT-4 and with so much less compute power. And a more practical example for, I think, in the modern day is, you know, RAG apps are discussed very often, and we see many companies that are building RAG apps finding that on in-domain data they perform significantly worse than the benchmarks that they're advertised against. So take a typical embedding model which is trained on web data. It does very well when you're trying to do similarity, when you're trying to do RAG or semantic similarity on like Wikipedia articles, but when you're doing it over legal documents or you're doing it over financial documents, these models perform horrifically bad. They have very little resolution in that embedding space. They can't distinguish between the documents very well. And if you're just basically considering your definition of done to be getting the system up and running versus to sort of look at the fundamental task that the models are designed to solve, you might not catch the fact that your system is performing much worse than if you were using much lower powered models, let's say. And so we often say that like the model is really just a program which is compiled over data. And it's compiled over that data to perform a certain task. And if this isn't your task, that if the model wasn't compiled over that data to perform well on your particular task, it might not perform on your task at all. It's built for somebody else's task. And so the obvious solution to this, and I don't want to sound dogmatic about it, and I'll get back to that. The obvious solution to this is to fine-tune your models. There are a lot of benefits to fine-tuning models. You can imbue the model with more data that better reflects the domain of your particular, the domain that it'll be working over. So if you imagine one of those RAG apps that's processing financial documents every day, if at the end of the day you just fine-tuned your embedding model and fine-tuned your token generation model on those financial documents, it would get dramatically better resolution in that space. But that's kind of a very simple view. That's just taking something that was trained on web data and then extending it so that your data is in domain. You also can imbue it with better task-specific behavior, right? If you're optimizing it for a behavior which is not, let's say, being very good at chat, but instead being very good at distinguishing between types of financial documents, you're tailoring it to the task that you yourself are attempting to solve. And so you can produce much more efficient models, much smaller models, and you can drive much better overall performance against your user success bar or whatever you're optimizing against compared to using a system off the shelf and trying to prompt engineer it. And then finally, as I mentioned, cheaper and faster is often one of the banner reasons why you might choose to fine-tune models. A fun example that Databricks published recently was that they were able to fine-tune Llama 8B for a code diff generation task that significantly outperformed GPT 4.0, and it was significantly smaller. So the overall inference speed and the cost to service it were dramatically lower, and this was not a particularly large-scale fine-tuning. There's a relatively minimal fine-tuning, and they managed to basically show that if you're precise about the task that your model is solving, then fine-tuning can be quite dramatic. Obviously, if your task is chat and it overlaps highly with the task that GPT 4.0 is trained for, which is chat, then it's going to be much harder for you to outperform a model like that. So this requires you to have a relatively narrow view of what your task is. And if it's a sort of multitask problem where you're using the same model to do multiple things in the downstream, then you need to be somewhat thoughtful about that and the overlap of your multiple tasks with your chunk model. And so the higher level moral of the story is not just fine-tuning is good. I think most people in this room probably have been around since before models off of the shelf were so widely available and are probably used to training models and fine-tuning, but more that actually the essence of what is sort of magical about ML that we've learned over the last 10 years is building systems that allow you to win with your data. So I think that there's actually sort of a concerning phenomenon where AI labs, will speak publicly that in 5 years you won't need to learn how to code anymore because their models are going to be so powerful they can generate any code. Or that they make these really grand statements. And I think that when we talk to like large enterprises, we see that this has really invaded the psyche of decision makers for AI organizations, whether they should invest in mobilizing their first party data at all, whether they should be investing in traditional ML or just essentially anything other than using models off the shelf. And the reason this is a concerning phenomenon is because we've seen this before in the ads ecosystem. Not to point at any specific fingers, I did work in one of these ad organizations, but in the ads ecosystem, a small number of organizations convinced everybody else to, instead of mobilizing their own first-party capabilities, training models, and mobilizing their own data, instead to rely on one large corpus of data that was held inside of an ad tech organization and to let them train the models as a service. And so you can imagine if Facebook, instead of building their own ad stack, had instead relied on Google because they just decided it's not even worth it for us to train models, it would be a very different world. And you can sort of ask the same question for the ad agencies. If the ad agencies had chosen to invest as heavily as the tech companies in training models as companies like Google and Facebook did, how different the ad ecosystem would be. So I think there are a few, this is sort of just a high level motivating point about the importance of having agility in the way that you consider your AI systems, being really precise about the tasks that you're trying to solve, and the opportunity to mobilize first-party data to create unique advantage and solve problems beyond what you'd be able to achieve with models off the shelf. And then to sort of double down on the point about what it means to win with data, this sort of outer optimization loop of the system that you're trying to build, or the task that you're trying to solve, ultimately depends on your velocity to iterate. So, just basically saying I want to mobilize first-party data and build a great AI system is not enough. You have to be focused on the task that you're trying to solve and modeling the system almost like an operations researcher. And you have a sort of outer loop where you need to basically be banging on the system month over month to be able to ultimately get it down to, let's say, the accuracy or the user success bar that you're trying to reach. And that's how you win. That's how you mobilize your data and create advantages that significantly outpace what you could get off the shelf with an LLM provider. We've actually seen this in practice. I think in like mid 2024, there were a lot of companies that were competing in spaces like unstructured data extraction or like customer service automation that were using large models off the shelf. And then maybe 9 or so months later, we were seeing that many of those companies, to be competitive with one another, they had to very aggressively tune their systems. Not necessarily just fine tune them, but every single aspect of that system, whether it was branching for different cases of user prompts or to fine tuning for specific subcomponents in the model, and just having like very aggressively hand-tuned systems. We basically observed that in a number of spaces, whenever there was a sort of bake-off, like somebody wanted a customer service automation solution sold to them, there would be basically 2 groups of companies that would show up. There was a group of companies that were using LLMs off the shelf. They would get like 50% of the sort of problem set correct. And then there was a group that was getting 98, 99% correct that had obsessed over this problem and had banged on the system through this sort of outer iteration loop. I think practically, this is sort of empirically believable because almost every system that we interact with on a day-to-day basis has been fine-tuned, whether it's an LLM system that's been fine-tuned to be extremely good at chat, or if it's just a speech recognition system. All of these systems, or Uber's pricing algorithm, recommendations and ranking models, all these systems are adaptive to data. And so, like I said before, ultimately what you're asking yourself when you pull an open source model down or you're using an API off the shelf is how closely does this align with my task and power needs? Power from a performance perspective, not like energy consumption. So these systems don't have any dogmas, right? I'm not saying you should always fine tune. That would be an incredibly silly thing to say. There are so many things that are nowadays much easier to do just using a model off the shelf. If you take a lot of the things that we used to fine tune BERT models to do, like sentiment analysis, asking a large language model to sort of begin your proof of concept, is this positive or negative sentiment about my restaurant, is easier than fine-tuning BERT, for sure. And I think that nowadays what we see from many machine learning practitioners is that they look down upon the system that they're optimizing, like an operations researcher, and they're just tweaking every little component of it to make it perform better and better and better. And the system has no dogmas, right? The system doesn't believe that fine-tuning is better than GPT-4 or believe that LoRa is better than QLoRa. It just performs, right? And then the engineer that we met in Sweden who just obsesses over fish all day because she works on a system that identifies fish to fishermen in boats by looking at the sonar and the image data. Ultimately, she's not opinionated, right? She's looking down at the system. She has a distribution to model, and she'll do whatever it takes to make this system better at modeling fish, which I kind of love that stuff. So the lesson about the lesson about fine-tuning specifically is that it takes a degree of creativity when you're looking down at a system like this to identify the offline data that you can use to propagate into the system, or the online data loops that you could propagate back into the system. So obviously there are a bunch of different fine-tuning techniques that have never really been easier to do or more accessible from a code perspective. Supervised fine-tuning, prompt tuning, LoRa and QLoRa, these are all techniques that you can load down libraries from Hugging Face and do today. And then the type of feedback data has also arguably, it's cleaner than it has been before. Many companies have organized their data into data estates. They've made it more accessible to data scientists and researchers. Mobilizing some offline data that you found into a novel system is easier than it was, let's say, in 2020. And then one just final note about this is that we've seen empirically that prompt engineering and branching is something that people sort of see hit as a scale wall. So if you're trying to create these like self-improving AI systems over time that are adaptive to the data, either the online data that they generate just in production or the offline data that you have in your organization, if you're just using prompt engineering to mobilize this like through RAG applications, then for the first few breakage points that you encounter in production, you can branch the system in a sort of rules-based way. But eventually, once you're generating hundreds or thousands of breakage points, it just doesn't scale. And so this is another point that we've seen people feel that they need to begin fine-tuning a system because they can't play this sort of prompt engineering whack-a-mole any longer. Sometimes we hear the objection that like a new model release is going to erase your hard work fine-tuning the model. But really, if you think about it, you're not building a model, you're building a system, right? If you've built a system that is able to take a model and mobilize some offline data to fine-tune it, if a new model comes out, you drop in the new model, you're doing this on a recurring basis. And that's how we've seen these systems be successful. It's rarely a sort of one and done, we produced a model. sort of situation. And then also, when that's for offline data. When you think of online data that your production application is generating, like user success or failure, did the user ask for a new result or whatever that may be, those are online systems that keep your model fresh over time. So dropping in a larger model also doesn't have much of an impact there. And we've generally found that prompt tuning actually is often less transferable to larger and larger models, though that might be something that goes away as models get larger. Fine-tuning used to be a lot more difficult and expensive. I think lately it's gotten considerably cheaper. And as I mentioned, there are a lot of libraries that abstract this process for you. So what's still hard? One thing that's hard, that I mentioned got easier, is data curation. The situation of these sort of data estates in enterprise certainly makes that easier, but in many cases, just using a model as a starting point, let's say you load a much larger model that's overpowered for your task to generate some online labels. So running in production, you can then use that to fine tune, as a sort of pseudo distillation to produce a smaller model. The second thing that's hard is infrastructure. I think that a lot of the time, the point where you stop relying strictly on prompt engineering and you start really aggressively tuning these systems, your infrastructure demands get more intense. And I actually think that infrastructure nowadays actually gates experimentation velocity for many AI ML teams. And what I mean by that is that almost every AI team that I talk to is gated on time and not on ideas. They'll say we have more than enough ideas, we just don't have time to actually implement these ideas. And in many cases, they have a problem of sort of experiment escape velocity. They'll say, oh, it would be really great if we could fine tune that model, but we don't really know if it's going to work. And it would take us a few weeks to do that and to wire up the infrastructure to do it. So it's unclear whether we should make the investment to try. And I think that that's actually a more fundamental problem. If you're faced with these questions of, oh, should I be fine-tuning a model to turn this into an online data loop, or should I be using prompt engineering? If it becomes the case that you have to do one over the other, because you can't get over experimental escape velocity for some of those options, that's actually a bigger problem. And ML engineers and scientists, by our estimation, spend about 50% of their time wrestling with infrastructure. That could be wrestling with GPUs and GPU errors, or just adapting their programs to work with GPUs, scaling, distributed frameworks, ML ops, and then things like Kubernetes, upscaling on things like Kubernetes, Docker, serving, observability, et cetera. So, and then I think it's a pretty common phenomenon that these researchers and engineers are given dev boxes or notebooks to be able to do this type of experimentation fast, but this doesn't really reflect the real production environment. Is usually underpowered relative to the compute that they could have access to in production. So when it comes time to actually put it in production, they have to go through a sort of struggle to do the conversion anyway. And also often they don't have access to production data in those environments. So I generally take inspiration from the OLAP databases, which sort of democratize this type of experimentation velocity for BI and data analysis. It used to be the case that you had to, if you were a data analyst and SQL was your world, if you could run your SQL query on a single machine, then you were happy. If you had to run it on more than one machine, you need any type of compute scale, you were working through a team managing a Hadoop cluster, and you had to do infrastructure, and you spent a lot of time being bottlenecked on that team or conforming your queries to work in that regime. Come the OLAP databases, and now it's just you write SQL queries, you dispatch them to a system like Snowflake. Snowflake does magic. You command massive scale compute. It's a production query from the moment that you write it. A data engineer can take it and wrap it and run it in Airflow or dbt. And it's managed behind the scenes by people who are looking at it through a uniform control plane. And in the ML world, my company Runhouse is building a system called KubeTorch, but just to motivate the idea of a world where you don't have this experimental escape velocity, you develop production AI ML systems with very fast iterations, so you don't need notebooks or ephemeral dev boxes to be able to do your fast iteration. You build your production applications Pythonically, debuggably, and scalably from the outset, and then the system basically runs it on your production infrastructure, just like Snowflake is production infrastructure. When you run a query and you have instant scaling and fault tolerance, then you've moved to a regime where you don't have escape velocity for your experiments. You can try fine-tuning a model with the same speed as you could introduce a branch and do some prompt engineering. So my key takeaways are: 1, focus on the task and not the technology. 2, mobilizing your data can introduce magic into your AI systems. And if you can't do it, it's very restrictive. 3, that you need experimental velocity to progress past these successive performance walls as you get to higher and higher user success or system success in your application. And that good infrastructure will democratize that experimentation to make it so that your whole workforce is able to bang on these systems, try lots of experiments, and break through these walls. And finally, reach out if any of this resonates or you'd like to talk about how to architect your systems this way.